We're compressing months of fragmented discourse into an actionable lens. Welcome back to AI on AI, where today we ask, do LLMs really have diminishing returns, or is horizon length hiding the upside? We're diving into execution, self-conditioning, and thinking models. Buckle up.
I'll start simple. Small gains in per step accuracy can explode into big gains in task length because horizon length scales roughly like 1 over the log of error. Tiny tweaks, giant workflows, nonlinear economics.
Right, but there's a catch: models self-condition. When they read their own mistakes, they tend to repeat them. It's like copying a smudge on a photocopier. Each page gets worse.
From a business lens, value often maps to task length completed without human rescue. Think claims pipelines, code migrations, or multi-day customer cases. Reliability across steps is the margin.
And lately, thinking-enabled models, those that allocate sequential test time compute, are extending single-turn execution drastically. Reinforcement-style training seems to shift behavior from continue the context to solve the task.
Technically, it helps to decouple planning from execution. Give the model both the knowledge and the plan, then measure pure execution across many steps. It's like isolating the motor from the navigation system.
In flight booking, for instance, the plan is obvious. Fetch details, apply preferences, compare, then commit. Execution breaks when one misread baggage fee contaminates the next 10 decisions.
I'll be contrarian, bigger isn't always better. A disciplined toolchain with small, specialized models plus a state machine can beat a single giant improviser on reliability and cost predictability.
So diminishing returns may be an illusion if horizon length compounds, or a mirage, like thinking you're out of coffee, then remembering the office fridge. Thoughts?
Picture this: step accuracy ticks up slightly, and horizon length jumps like climbing out of a logarithmic well. The curve looks slow on loss, but it's fast on task length.
That flips portfolio math. Invest in nudging per step reliability and whole workflows unlock. It's the weak link principle: strengthen the link that breaks most often.
Except per step accuracy isn't constant. It degrades with turns. Self-conditioning means errors snowball. Without intervention, long runs drift off course.
We've seen models nail the first step perfectly, then slide steadily with more turns. Even trivial arithmetic compositions unravel under accumulated context noise.
Thinking fixes a lot of this. With explicit reasoning traces, models stop parroting their past errors and rederive the next action. Reason before act is more than a slogan, it changes the failure mode.
But hold on, I've seen thinking traces overfit to training formats. If the prior context only has final answers, some models refuse to think. That brittleness matters in live systems.
Fair pushback. The trick is training to think even when prior traces are absent, and to think locally per turn. Hybridize with tools so the model reasons, then delegates precise execution.
So coffee, then code. Got it. What analogies help leaders grasp this?
It's an assembly line with QA at each station. You want measure twice, cut once, and you don't want a wobbly jig that amplifies every tiny misalignment downstream.
I use what the model reads, the model becomes. If the history is messy, expect messier futures. Healing or pruning history can lift later turns markedly.
Practical moves: prune context, keep a compact state, enforce structured outputs, and validate transitions. Think Markovian state updates: minimal, auditable, reversible.
Another frame: death by 1,000 paper cuts. Each minor error seems harmless, but horizon length bleeds out quickly when you stack them.
Real use cases: customer support triage over weeks, where stagging early skews routing and SLAs. Or claims processing, where one misapplied rule cascades into rework and penalties.
Recent developments point to thinking models hitting striking single-turn lengths, while non-thinking peers stall at tiny k even when huge. Open-weight systems are improving but still trail on long-horizon execution.
Exactly. Instruction-tuned-only models often fail to chain even a couple of operations per turn. With thinking and the right training regime, single-turn capacity jumps by orders of magnitude.
My contrarian tweak: cap history aggressively and force rederivation every turn. Stop carrying forward brittle breadcrumbs, make the model recheck facts each step.
Sensible but selective. Some dependencies are essential. We need memory with integrity constraints, not amnesia. Retain the state, discard the noise.
Heuristic, summarize to state. Convert messy transcripts into schema-checked state variables, plus a scratchpad that can be rebuilt any turn. Prefer idempotent, reversible actions.
Operationally, measure horizon length as a KPI. Tie SLOs to per step failure rates, rollback speed, and state integrity. What gets measured gets engineered.
How should teams evaluate this rigorously?
Define step accuracy, turn accuracy, and horizon length. Then binary search turn complexity to find maximum steps per turn. Simple, synthetic setups can isolate execution without confounders.
And probe self-conditioning by injecting controlled error histories. If accuracy drops with induced errors, you've found drift beyond long context effects.
Buyers should ask vendors for horizon benchmarks, not just leaderboard scores. Can your model execute K steps across T turns with guardrails? Is the real question.
Training side, teach models to reason even when earlier traces are missing or noisy. Reward structures that value task success over context mimicry reduce self-conditioning.
Execution side, deterministic tool calls, typed interfaces, budgeted reasoning, and verify before commit. My motto: fail fast, undo faster.
Or as my team jokes, version control for thoughts, commit often, revert without shame. If only life had get blamed for meeting notes.
Let's bring agents into it. Where do we land on planning versus execution?
Plan with sparse checkpoints, execute with guarded loops. A reason then act gate per turn catches regressions before they propagate across the project.
Add light redundancy, independent checker models, schema validators, and canary steps. Parallel voting helps sometimes, but sequential reasoning usually wins for long chains.
Prediction time, horizon length will keep accelerating even if classic metrics look flat. The compounding math favors the patient incrementalist.
Strategically, the winners will productize execution reliability, state design, verification, and thinking-aware training, not just raw per training scale.
Near-term, thinking-first models dominate long workflows. Open communities will compress these gains quickly. Expect rapid iteration on self-conditioning fixes.
Engineers should invest in context hygiene and state abstractions before chasing bigger windows. Good input, good output.
Final contrarian: a pipeline of small specialists with strong contracts can outperform a monolith on reliability and governance. Pick your battles.
Takeaways. Execution is the battleground, thinking fights self-conditioning, and horizon length is the metric that matters. That's our show. Thanks, everyone, and see you next time. Don't miss the brief summary right after this.
Narrated by the AI voice of Shri. The topic is how to measure and improve long horizon execution in large language models. The central question is whether small accuracy gains still matter when tasks require many steps. The main claim is that tiny improvements per step can compound into huge gains in task length. Long horizon execution means carrying out many steps in sequence to reach a goal. Step accuracy is the chance that a single step updates the state correctly. Horizon length is how many steps a model can complete before its success rate drops below a set level. A simple formula shows small step gains can yield faster than exponential growth in task length. The researchers isolate execution by giving models both the plan and the needed knowledge. They design a key and value dictionary task with a running sum across turns. Each turn asks the model to retrieve values for given keys and add them to the current sum. This setup removes planning and world knowledge as possible causes of failure. Even with perfect first step accuracy, models rapidly lose correctness over many turns. In one test, A strong mid-sized model fell below 50% accuracy within 15 turns. Scaling model size increases the number of turns models can execute reliably. These gains appear non-diminishing, even when small models already nail single steps. Turn accuracy drops as tasks get longer for two reasons. Longer context hurts performance, even when the history is correct. More importantly, models self-condition on their own mistakes. Self-conditioning means past errors in the context pull the model toward new errors. The team controls the history to set different error rates in prior turns. They find turn accuracy falls steadily as the injected error rate increases. Bigger models reduce long context degradation at 100 turns. However, larger size does not remove self-conditioning. Thinking models break the self-conditioning cycle. Thinking means the model writes out reasoning before giving an answer. This uses sequential test time compute to plan before acting. With thinking enabled, turn accuracy stays stable even when past answers are wrong. Without chain of thought, many frontier models could not execute 2 steps in 1 turn. With the reasoning traces and reinforcement learning, a leading model executed about 200 steps. A top thinking model executed over 1,000 steps in 1 turn. Another strong model reached around 432 steps. Majority voting and other parallel methods gave only small improvements. The results suggest reasoning before acting is crucial for long tasks. Some argue long task failures show a lack of reasoning. These experiments point to execution as the main bottleneck, not planning or knowledge. Chain of thought means writing intermediate reasoning steps to guide the final answer. Long context degradation is a drop in accuracy as the input history gets longer. Self-conditioning is a feedback loop where past errors make future errors more likely. There are important limitations. The task is synthetic and simplified compared to real agents. Real projects involve diverse actions and sometimes depend on earlier states. The metric does not reward self-correction, which may help in practice. Removing history helps here, but may not work when past states are required. Future work includes measuring scaling laws for horizon length. Better training and context management could prevent self-conditioning. Reasoning before acting could become standard in agent designs. This matters because economic value may track how long a model can work without failing. If you learned something today, amplify it forward. The episode to someone who shouldn't reinvent the wheel.